Hello everyone, I am Anmol and today I am going to show you how different LLM frameworks can be used to transition from prompts to CAD models. A lot of the inspiration for this video came from developing the Ant plugin, which also incorporates LLMs. As Ant is based on Grasshopper, which is basically a visual programming interface, the current video will use Grasshopper interface in its examples, but regardless, the main concepts present in this video are applicable to other CAD platforms as well. So let's begin. First, I would like to show the simple algorithm to create a twisted tower, which will be used as an example throughout this video. We start by creating a base geometry which is taken as a hexagon. Then we make multiple copies of this base geometry and stack them vertically. After this, we will scale each hexagon to be 90% in size of the hexagon below it, and similarly, we will rotate each hexagon around its center so that it is 30 degrees rotated with respect to the hexagon below it. And finally, we will create a surface connecting all these hexagons to create a final twisted tower. This is the CAD workflow that we will use to create the twisted tower, and we will see how different LLM frameworks can be used to create this algorithm. In order to design an LLM framework, the first thing is to define the tools that the LLM should have access to. These are the tools through which the LLM can interact with your CAD environment. These can be MCP servers, API frameworks, RAG models, or any other custom made functionality that the LLMs can use for CAD modeling. While you can define any number of tools with different purposes, we will keep it simple in this video and we will work with just two tools. The first one is the read tool. Through this, the LLM can read the current state of your model. It tells the LLM what geometry is already present in your environment, and it can use that information to build upon the existing model. The second one is the write tool. Through this tool, the LLM can emit operations which will be implemented in your CAD environment. For example, if the LLM wants to move an existing geometry, it can use the write tool to emit the move operation which will be implemented in your model. This way, the LLM can make changes to your CAD model. One thing to note here is that defining the tools is not sufficient. We need to instruct the LLM on how to use these tools and what functionality is available at its disposal. All of this is included in the tool descriptions that is sent to the LLMs and form a part of their input context. We will start with the simplest LLM framework where we will use just one LLM agent to create the twisted tower. We start with an existing base geometry of the hexagon and the user enters the prompt. The prompt along with the read and write tool descriptions is sent to the LLM. The LLM first uses the read tool to inspect the current state of the model and discovers the base geometry already present. The read tool provides other valuable information to help the LLM build on top of the base geometry. Following this, the LLM proceeds to create a step-by-step plan on how to create the twisted tower. And finally, the LLM uses the write tool to execute that plan. With the write tool, the LLM can create components and connections to the existing base geometry. It emits these operations which are implemented in the CAD environment step by step. With this workflow, the LLM is able to translate the prompt into a CAD model. Here you can see that we are using the same LLM agent to perform multiple tasks. It has to use the read tool to inspect the current state of the model. It has to break down the request into smaller steps, and also it needs to execute those steps. All these roles that this single LLM is playing actually require very different skill sets. For example, breaking down the user prompt into smaller steps is a very cognitive intensive task and needs complex reasoning capabilities. Whereas the execution part of the work is not very complex as the plan is already prepared, but it needs a high degree of accuracy to correctly use the right tool to translate the plan into operations. If we use a single LLM to perform all these tasks, we run into the risk of cognitive overloading. This essentially means that LLMs perform well if they are assigned only one type of job. If we ask a single LLM to perform multiple specialist jobs, then it does not perform well on either. The other major drawback of this approach is that each LLM has a limited context window, which means that we have to be careful of the input data that we send to the LLM. We are asking the same LLM to use all the tools at our disposal. And for that, we need to give it the tool descriptions, which explains the LLM on how to use these tools. These tool descriptions eat away a huge chunk of the context window. Such a system won't scale well because with increasing the number of tools, we run the risk of context overflow where we exceed the context window of the LLM. The very first version of Ant actually used this simple LLM framework, but since has improved as we will see further. Okay, now let's improve the LLM framework. Instead of having a single LLM do all the tasks, we will divide the workload between a planner and an editor LLM. Let's see how that will work. Again, we start with the base geometry and the user prompt. Now, this input is sent to a planner LLM. The role of the planner is to interpret the user prompt and make use of the read tool and output a step by step plan for the editor to implement. Note that the planner is given access to only the read tool and not the write tool. So after the planner has created the plan, it is sent to the editor LLM, which implements this plan using the write tool, which is further executed in the CAD environment to create the twisted tower. In this way, we can separate the roles between the LLM agents and manage their context. Each LLM agent is only responsible for a specific task. This already improves the performance of the LLM framework significantly. This framework is most suited for one-shot edits where the user wants to build geometry in small steps. Separating the roles handles the cognitive overloading and context overflowing issues to a huge extent. Another huge benefit of this framework is that it is very cost effective. In fact, this type of LLM framework was actually present in a previous version of Ant. But even this framework can be improved. Right now, a crucial thing that is missing in this framework is a feedback loop. The LLM does not review its own output and iterate over it. In order to have the LLMs perform tasks autonomously, we need to refine this framework. Let's see how we can handle a feedback system in the Planner Editor framework. Again, we start with the base geometry and a user prompt. The prompt, along with the read tool instructions, are sent to the Planner LLM, which examines the current state of the model using the read tool. Now, instead of implementing everything in a single go, the planner builds the model in small steps. It creates a plan to only partially create the twisted tower with only the move and scale steps. The editor gets this plan and executes it to create an intermediate state of the twisted tower. Now the flow goes back to the planner where it inspects the work done by the editor LLM. Only once it has verified that the previous implementation is correct, that it goes on to plan the rest of the steps to complete the twisted tower. Then the editor implements that and completes the model. In such a system, we build the model in small subsequent steps and only proceed to the next step once the previous step is verified. This framework is well suited to catch modeling errors while the model is still being built. For instance, consider this example where in the first modeling step, the editor LLM uses an incorrect scaling factor such as 1.1 instead of zero point 0.9, and this is reflected in the intermediate geometry that is created. In such a case, the planner can catch such an inconsistency while inspecting and first have the existing model corrected with the right scaling factor. Once that is executed by the editor and the planner has verified the change, then it can proceed on to build the remaining tower. This is a much more robust framework and it can also handle complex tasks autonomously. In fact, the current version of Ant uses something similar. But this sort of a system also comes with its own challenges. The biggest challenge is context compounding for the planner LLM. The editor is a one-shot LLM agent where it simply has to execute the plan provided by the planner. But the planner needs to keep track of the previous implementations so that it can step by step reach to the final geometry. So the results of each iterations are sent along with the input to every subsequent planner call. And with this, the context can compound significantly. A lot of LLM models support context caching to deal with this issue. Despite this, the feedback loop lends a lot of robustness to the overall performance of the LLM framework. So let's summarize what we have seen so far. We looked at a couple of LLM frameworks. The single shot LLM, where a single agent does the planning and execution. It is a simple design, but it can run into cognitive overloading and context overflowing issues. To resolve this, we introduced the Planner Editor framework, where we divided the roles into different LLM agents. Such a system works well for individual small edits. And finally, we introduced a feedback loop and modular implementation to the Planner Editor system to make it more robust. This system is able to autonomously work on bigger tasks. Ant is under active development, and we are constantly working to improve the underlying LLM frameworks, as this is the main engine that powers the plugin. If you have any thoughts about this, then let me know in the comments. And also, do not forget to check out Ant. That was it for this video. See you next time.